So, the theory or idea that it proposed centralizes on the fact that the space might be a curvature or fabric of space-time. Yes, you heard it right. So, flashing back in 1600s, when Sir Isaac Newton gave his famous and authentic Newtonian mechanics, he gave the idea of gravity to the world. He wrote about the objects pulling each other through space with some sort of force, which he named as gravity. Due to not much technical advances at that time, he wasn't able to prove it experimentally, but still he proved it mathematically, and it is significant by now. But what we know that Einstein explained it totally differently. He mentioned space as a fabric, also gave it an amazing and wondrous adjective of being flexible. He explained further that the space is flexible, so at higher masses like planets or big stars like Sun, it warps the environment of space-time around it. In a sense, a space warps allow you to distort space-time around you. More massive objects such as black holes create bigger bulging pockets of space-time, while teeny objects such as spacefaring human would just barely represent a dent. So this explains that gravity may be everywhere in space. So looking at an interesting aspect that even a what could we say hmm, mass that even a mass that is like millions of light years away from the source of gravity would also be affected by the gravity produced by that source. Interesting, huh? And definitely the gravity will be almost negligible. You can find it by accounting the universal formula of gravitation, uh, that is given as the force F is equal to the gravitational constant multiplied by the mass of the planet or source and the mass of the object divided by the square of the radius of the planet. I think that explains our solar system. I know it might not have been clear fully, so let's look at a better example which will definitely clear your doubt's face. And let me tell you, there's nothing better than a trampoline when it comes to general theory of relativity. So let's assume space-time as a trampoline. You must be thinking that, Aryan, why there's a need of so much assumptions? Let me clear it. When you're studying advancing in physics, most things are taught by examples and assumptions. Because we definitely can't arrange cosmic creatures, I would say, according to our need. Definitely can't. So thinking space-time as a trampoline, and you put a heavy object in the middle of it, you will suddenly see the object warps the space of the trampoline around it, looking something like this. This indent would be stronger near the middle and it would be weaker near the edges. If you were to place a small ball into a trampoline, it would roll towards the middle. By Newton's law of universal gravitation, it would say that the ball was attracted to the heavy object, but by general relativity, the ball would be following the curve of space-time. If you look the same framework at a very big aspect, same thing happens in our space, solar system and all. Sun warps the environment and then the planet go into an orbital trajectory. Now I think it must be making a total sense to all of you, cause I know in our whole school or high school time we are taught about the idea of gravity that is given to us by Sir Isaac Newton, and definitely this is a big change. While general relativity has been more precise, Newton, grav- uh, Newton, uh, Newton way of gravity is still incredibly accurate and can be used for simpler situations. On the other side, general relativity uses more complex calculus that makes it difficult to compute. But Einstein has opened the world to the complete new physics, and it's the complex one, like black holes and gravitational waves, that continues to develop our understanding of the universe. Also, Einstein theory wasn't taken serious and wasn't taken into notice at that time. To be first, it was thought as joke to the people at that time. In 1916, Einstein came up with the idea that if the space is flexible enough to warp, then it should be able to produce ripples or undulate to produce waves. So that basically means if something jostles the fabric of space-time, it would produce or send out the ripple to the fabric. It would produce ripples towards the space-time. He then made a point, and these ripples are what we today call as gravitational waves. Gravitational waves should also be emitted when two black holes collide. As they spiral in towards each other, they should emit a burst of gravitational waves with a particular signature, I would say. Provided the collision is sufficiently close and sufficiently violent, it may be possible to observe them with instruments present on this earth. And these instruments has to be really precise because the changes that we get on our earth is really at the uh, fraction of the atomic scale. So the devices, our devices has to be really particular and precise. And as of quick news, physicists had discovered that around 5 years back in 2016, the success of the ultimate LEGO team. We will talk about the gravitational waves later in this course. So I like to end this video right now, and I hope this would have been informative. See you in the next part.